I'm Pavel Koten from the Astronomical Institute of Czech Academy of Science in Ondřejov, and I will add another talk about the Tau Herculid meteor shower. But contrary to other talks, this one will be based on the data which were recorded in Europe. So, as you already know, there was a breakup of the comet 73P Schwarzmann-Lachmann 3 in 1995, and several models under assumption of higher ejection velocities predicted that the ejecta could get close to the Earth on May 31. The maximum was predicted for early hours UT, so which was preferable for North America. On the other hand, there was a prediction by Wiegert et al. That there is a possible activity from older material, which was released from the parent comet at the end of the 19th century. And this activity was predicted to be observable before midnight or around midnight, May 30 to 31. What means that it would be observable in Europe. So when we decided about our observation strategy, we decided not to go to US as other teams did, but be ready to be ready for mobile expedition across the Europe, depending on the weather forecast and actual weather conditions. Our goal was to cover possible earlier activity of the outburst and or activity of older material, and also to look for some meteor pairs or meteor clusters, as this is one of our ongoing project. We have frequently updated models from the Czech Hydrometeorological Institute, and it led us to final decision to stay in the Czech Republic. One of the benefits of this decision was that we can use the background of the Czech Firebolt network, and we were able to establish 2 sea-station video experiments to increase the probability of clear sky, even if one of the station would be overcast. We have still chance to make a double station observations. And finally, the predictions were forecast predictions were quite good for the Czech Republic. Our double station video experiment is usually carried out on the base Ondřejov Kunjak, and we use all these stations again, and moreover we add 2 other stations. For the west field, we employed Maya cameras, which use image intensifiers and 50mm lens, providing field of view of about 52 degrees. Third station was on the west and employed 4-megapixel IP camera and another photography camera. On the east field, we aimed DMK cameras with image intensifiers and long focal length lenses, Canon 135mm, which provides field of view of 22 degrees. And there was also third station, again using 4-megapixel IP camera and photography camera. And of course, everything was inside the Czech Firebolt network. So the photography cameras of this network and other IP cameras at some of the stations were ready. Altogether, we were able to observe 5.5 hours starting at 20 UT. At the beginning of the observation, the conditions were cloudy at the southern part of the Republic, but later all the stations became clear, and all the cameras were able to record. Altogether, we have almost 300 video meteors. 170 of them were classified as Tau Herculids. 120 were single stations, and almost 50 of them were double station Tau Herculid meteors. So firstly, we calculated activity profile. We tried different time intervals, but the best curve looks for 30-minute counts. We use all single and double station Tau Herculids. The counts were corrected only on the zenith distance of the radiant, and the resulting quantity is called corrected hourly rate. Please do not compare this with visual ZHR. This is not a directly comparable value. The activity started to increase after 21 UT. At the beginning, it was cloudy at the south, so the cameras at the south didn't contribute, but between 23 and 1 UT, the activity was quite stable. It fluctuates between 60 and 70 meteors per hour, and some maximum can be observed just before midnight. After 1 UT, it started to decrease. It was because of partly because of dawn. So for the double station meteors with complete light curve, so we can determine photometric mass. It's for 48 meteors, and using the plot of logarithm of photometric mass versus a logarithm of cumulative number of meteors, so we try to determine mass distribution index and population index. But it's quite difficult to determine cutoff point when the faint meteors start to be undetected, and the values of the indices are not yet exactly determined yet. At this moment, we can say that the mass distribution index is about 1.9 and population 2.3. When compared with visual observations as reported by Renter and Art, it's a bit lower. They found population index to be 2.6 for earlier part of the shower activity. Our observations cover a relatively narrow range of masses, and we hope it will be improved when photographic meteors will be added because they are of bigger masses. Of course, having double station observation, we compute atmospheric trajectories and geocentric orbits, and these were compared with JPL elements of comet Schwarzmann-Wachmann 3, and using Southward-Hawking D criterion, the shower membership was determined. We can also look on the geocentric radiance of the meteors, and which are plotted here, and you can see that there is some concentration of the radiance about the values of models prediction by Hori and by Vobalion, but it's interesting that those predictions were for the 1995 comet breakup. There are also some dispersed radiant to lower right ascension and declination. We tried to find if there is some relation between the position of the radiant with the solar longitude, photometric mass, semi-major axis, or perihelion distance, but didn't find any relation. It seems that this dispersion is real. Another check was if these dispersed orbits are not the orbits with poor DSH criterion, but as you can see in this plot, among the dispersed radiants are not only poorer orbits, but also orbits with better determination. And on the other hand, among the predicted radiants, there are also some poorer orbits. So again, it seems that the dispersion is real. So let's summarize our result. So we observed broad maximum of activity by video cameras before the midnight, which is consistent with the visual observations, which report that there was a yearly maximum around 23 UT, is the width of 3 hours. This activity could be connected with material which was ejected from the comet at the end of 19th century, as modeled by Wiegert et al. It could suggest that it is a really older material. Again, the partly scattered radiants could also be in agreement with this. And finally, because we didn't detect any meteor pairs or meteor clusters, which is typical for older streams, it's again some support for the idea that we observed rather older material from the end of the 19th century. So that's all, and thank you for your attention.